So in order to perform this translation of virtual addresses to physical addresses, we use what's called a page table. And a page table has an entry for each virtual page. So the number of entries is the number of virtual page numbers. Each entry in that page table has a valid bit and the physical page number where the page is located. If it's invalid, it means it's not mapped to physical memory or main memory. So here's a page table example. Here's our page table right here. And so in this case, we have, our virtual page number, 19 bits here. So our number of entries in our page table is, it's not showing all of them obviously, is 2 to the 19 entries into that page table. Okay. And so we use our virtual page number to index into that page table. So in this case, for address 247C, virtual address 247C, which is produced by our processor. We look at the page offset. We're not translating, so we're just looking at the virtual page number, which are those upper 19 bits. And this is 2, so we look at entry 2. And entry 2 is valid. It says, yep, this is mapped to physical memory or main memory. And we find the physical page number, or that translation that we just used in that prior slide. And so we read that from this memory. We look at the valid bit to say if it's valid, if it's a hit. Yep, it is actually in physical memory. And we use that physical page number and then append our page offset to give us the physical address. So given this page table, what is the physical address of virtual address hex 5F20? Try it on your own, and then we'll do it together. So the page offset is, again, the lower 12 bits because our page size is 2 to the 12 bytes. And so here's our page offset. We don't translate that. Again, all we're translating is our virtual page number. So we look at this table. We look at entry 5 because it's virtual page number 5. It is valid. That means that page is mapped to main memory, to physical memory. And the translation, the physical page number is hex 1. And so now that's our physical page number. And we append that with our page offset to get the physical address. So this is our physical address. Translation of virtual address hex 5F20. Here's a second example. What's the physical address of virtual address hex 73E4? So again, we just look at the upper bits. These lower 12 bits are the page offset, so we don't look at those 12 bits because those will stay the same. This is basically which word within that page we're looking for. We use the virtual page number, the upper 19 bits, to look at page or entry 7 in the page table, and we see that it's invalid. So that means that this page is not mapped to physical memory. So the system would need to then pull that page or choose a page in physical memory where it would like to write this virtual page. So this is a miss in the system from in the main memory system. So the term we use for pulling this page into physical memory is called paging, or sometimes called swapping, when it has to swap out another page. It's really large, and it's usually located in physical memory because it's so large. So load or store requires not just one memory access, but 2 memory accesses. One to read the page table, to do the translation from virtual to physical memory, and one to actually access the data once it gets the physical memory address. So this cuts memory performance in half, unless we get a little bit clever.